Right now, there is actually an AI running, well, potentially running entirely inside your smartphone. And it is mathematically smarter than the supercomputers that, took us to the moon.
Yeah, it's pretty staggering to think about.
Right. And it doesn't even need an internet connection to function. But the funny thing is, if you try to figure out what it's actually called or how it works, you just hit this absolute wall of acronyms.
The alphabet soup is real.
It is. You see GPT, BERT, LLaMA, Phi 3, and if you're anything like me, you see all those letters, and part of your brain just shuts down. It's incredibly overwhelming.
I completely agree. I mean, we are living through this massive flood of innovation right now. And honestly, the engineering naming conventions are not doing the public any favors at all.
No, they really aren't.
Half of these models sound like droids from Star Wars, and the other half sound like obscure collegiate fraternities.
Exactly. And you sit there wondering, like, am I supposed to know what all of these do? How do I even begin to categorize them? And that really is why we are doing this deep dive today.
To finally clear that up.
Yeah. Our mission is to cut through that noise. We want to act as your shortcut to actually being well informed on this stuff. We've spent the last week dissecting this really dense stack of technical notes and architectural breakdowns that categorize large language models, or LLMs.
Yeah, and we're going to move way beyond just memorizing an intimidating list of acronyms, right? Because that doesn't actually help you.
Right, exactly. We are going to uncover the actual why and how behind their designs.
Which is such a crucial shift to make. Categorizing these models isn't about, sorting them into neat little boxes. It's a much deeper exercise in understanding their mechanics.
You have to look under the hood.
Exactly. We have to look at their architecture, how they're trained, what kind of data they can actually perceive, and this is a big one, their physical footprint.
Right, where they literally live.
Yeah.
Yeah.
Because this framework is the absolute key to matching the right model to the right task. I mean, not all AI is built to solve the same problems.
Okay, so before we can even talk about what an AI knows, we have to look at how its brain is fundamentally wired, the blueprint,
The
right?
structural foundation, yeah.
And the underlying foundation of almost all modern LLMs is something called a transformer architecture. Now, I have to be honest with you. Whenever I hear transformer, I just picture a giant Michael Bay robot.
You and everyone else.
Right. So what is actually happening mathematically here? What makes a transformer a transformer?
So the defining feature of a transformer is something called the attention mechanism.
Attention mechanism, okay.
Yeah. So before transformers came along, AI read text very linearly. It would read a sentence from the beginning to the end, and by the time it got to the end, it kind of it forgot what happened at the beginning.
Like a really short attention span.
Exactly. But a transformer doesn't do that. It looks at a whole sequence of text and assigns mathematical weights, or, attention, to every single word's relationship with every other word.
Wait, regardless of how far apart they are in the sentence?
Yes, exactly. Distance doesn't matter.
Okay, let's unpack this a bit. Give me an example of how that actually changes things in practice.
Okay, take the word bank.
Like a money bank.
Well, that's the thing. If I say I sat by the bank of the river versus I deposited money at the bank on the corner.
Oh, I see.
Right. The word bank means two entirely different things.
Totally.
A transformer uses its attention mechanism to weigh the word bank against the word river or the word deposited and instantly grasps the correct context.
Got it. Okay, so the transformer is the bedrock. That's the baseline. But within that transformer world, there are distinct variants, right?
Yes, several different blueprints.
And the first blueprint we need to look at is called decoder-only. And the technical term in notes for this is autoregressive.
Yeah, that's the one.
Now, autoregressive sounds like a faulty transmission in an old car or something. What is the actual mechanism there?
It is a very heavy, jargony word, but the core concept is actually really straightforward. A decoder-only model generates text sequentially, literally from left to right.
Just one word after another.
Exactly. It looks at the words that have come before, and it calculates the mathematical probability of what the very next word should be.
Just the one next word.
Just the one. It predicts that one word, outputs it, and then runs the entire massive calculation all over again for the word after that.
I was trying to picture this when reading the notes, and it feels like an incredibly fast, maybe highly caffeinated improv actor.
Oh, that's an interesting way to look at it.
You know that game where the audience yells out a starting phrase and the actor just has to build the story one word at a time?
Yeah.
They have no idea how the sentence is going to end when they start talking. They're only basing their next word on what they literally just said a millisecond ago.
That is surprisingly close.
Yeah.
But to make that improv actor perfectly accurate to the machine, you have to imagine they also have a massive calculating spreadsheet inside their head.
So they aren't just winging it.
No, they aren't just guessing randomly. For every single step, they are rolling a million-sided die where every side is a word in the English language.
Wow.
And the weights on that die constantly shift based on the previous words.
Yeah.
But yes, the left-to-right generation, the improv aspect, that's exactly how it works.
So my smartphone autocomplete, like when I type, I am running to the, and it suggests store. That's essentially a very primitive, microscopic version of a decoder.
Precisely. That's exactly what it is. Now just scale that up exponentially.
Right.
Because of this predictive, forward-moving momentum, decoder-only models are absolutely ideal for tasks that require generation.
Generation, like creating new text from scratch.
Yeah, think chatbots or creative writing. They excel at keeping a conversation flowing forward.
Because they are literally built to just keep the ball rolling, which
Yeah.
makes perfect sense why GPT-4 and LLaMA fall into this category. Those are the models you and I are actually having back and forth conversational chats with.
Right. But there is a massive inherent flaw in only moving left to right.
Oh, which is what? Does the improv actor lose the plot?
Exactly. They completely lose the plot. If you are only ever looking backwards to predict the immediate future, you really struggle to grasp the overarching context of a massive document from a bird's eye view.
Because you can't read ahead.
You can't. You're blind to anything that hasn't happened yet.
Which brings us to the architectural opposite, the encoder-only variant. And this one is described in our sources as having bidirectional context.
Right, bidirectional.
So it's not just moving left to right. How is it actually looking at the data?
An encoder-only model looks at the entire input sequence simultaneously, left to right and right to left.
So all at once.
Yes. It absorbs the surrounding context of every single word before it makes any output decisions at all.
So if the decoder is the improv actor reacting in the moment, the encoder is like a detective solving a murder mystery.
Oh, I like that.
How so? Well, if you are a detective, you can't figure out who the killer is by just reading the first chapter of the case file linearly, right?
Right, you'd miss all the later clues.
Exactly. You have to look at the bloody footprint in Chapter 2,
Yeah.
the alibi in Chapter 5, and the motive in Chapter 10 all at the exact same time to realize that the butler is lying.
That's a great analogy.
You are mapping all the clues simultaneously to understand the big picture.
That is a much better way to visualize it, yeah.
Oh.
You are establishing the complete, interconnected web of meaning.
And because it understands the whole picture at once, I'm guessing it's used for different things.
Definitely. Encoder-only models are unparalleled for understanding tasks rather than generating tasks.
Understanding tasks, meaning things like sentiment analysis.
Yes, exactly. Let's say you need an AI to read 10,000 customer reviews and tell you if people are generally happy or furious.
You don't want an improv actor guessing word by word.
No, you'd get terrible results.
Mhm.
You want the detective to read the whole document at once to understand the nuanced context.
Right.
It has to know that a sentence like, "The service was terribly good," is actually a compliment, even though terribly is usually a really negative word.
Because the bidirectional attention maps terribly directly to good, shifting the entire meaning.
Exactly.
And the classic example here is BERT, right? That was the model that fundamentally changed how search engines actually understood our weird, messy human queries.
It was the massive leap forward. BERT didn't just match keywords. It read the whole search query at once to really understand the intent behind it.
Okay, so we have the improviser generating text the decoder. We have the detective understanding text the encoder.
Right.
But obviously, there are times when you need an AI to deeply understand a massive document and then generate a completely new, coherent response based on it. How do we get both?
Well, you combine them.
Just mash them together.
Pretty much. That is the third architectural variant, the
Yeah.
encoder-decoder, which is also known as sequence-to-sequence, or C2C.
C2C.
It is the ultimate synthesis. It handles complex input processing and complex output generation.
So it solves the murder mystery first and then starts doing improv about it. How do the two halves actually talk to each other without getting confused?
So the encoder takes in the original text and processes its full bidirectional context.
It reads the whole room.
Right. And then it condenses all that complex meaning into a dense mathematical representation, often called a context vector.
A context vector.
Yeah. Think of it as the pure, distilled mathematical essence of the document. Then it hands that essence over to the decoder.
Oh, I see.
And the decoder takes that deep understanding and generates a brand new sequence of text left to right.
I am picturing a professional translator sitting at the UN.
Okay, yeah.
If you hand them a highly technical 50-page legal contract in French, they don't just start translating the very first word into English immediately. That would be a disaster.
They would lose the nuance immediately. The grammar wouldn't even line up.
Right. They read the entire French document first. They act as the encoder, absorbing the full context, the legal loopholes, the overarching tone. Then they distill all of that into a mental concept of what the document means. Finally, they pull out a blank piece of paper and act as the decoder, meticulously drafting a brand new, perfectly constructed English version from top to bottom based on that mental concept.
Which is exactly why encoder-decoder models are the industry standard for tasks like translation or high-level summarization.
Because you need both skills.
Exactly. If you want an AI to read a 40-page research paper and write a tight 3-paragraph summary, you absolutely need the C2SIG architecture. Models like T5 and BERT are the heavy hitters in this space.
Okay, so we've got the blueprints down. We know the underlying math of how these transformer brains process information. But a blueprint is just an empty building.
Right. It doesn't do anything on its own.
Exactly. An architecture doesn't actually know anything until you teach it. Which brings us to the curriculum. How do we train these architectures to actually be useful?
So training generally splits down 2 main paths. The first path is what we call zero-shot or general-purpose models.
General purpose.
Yeah. These are the models designed to be ready for broad, incredibly diverse tasks right out of the box without any extra hand-holding.
The ultimate generalists.
Right. During their initial creation, they are pre-trained on a staggering amount of data. We're talking about massive scrapes of the entire public internet.
Like Wikipedia, millions of books.
Articles, forums, basically everything text-based we've ever uploaded. And because they have ingested so much varied language, you can ask them to write a sonnet or explain quantum physics or give you a recipe for lasagna, and they can do it reasonably well.
But wait, if I have a model that knows literally everything on the internet, why would I ever want anything else?
What do you mean?
Well, if a generalist can do it all, isn't that the finish line for AI development? Why is there an entirely separate category for fine-tuned or domain-specific models?
Because the internet is full of garbage.
Okay, fair point.
Think about it. A generalist model is basically playing a numbers game across human knowledge.
Right.
If you are an architect designing a skyscraper, you don't want a model that gives equal mathematical weight to a highly technical structural engineering manual and, a random Reddit thread where someone is arguing about how to build a shed.
Ah. You want the expert. You want the neurosurgeon, not the general practitioner.
Exactly. So you start with that base model, the generalist that already understands grammar and basic reasoning, and then you put it through fine-tuning.
How does that work?
You give it highly specialized, intensive training on a very specific niche of pristine data.
Right.
By doing this, you physically alter the weights and parameters inside the model, so it prioritizes that specific domain over general chatter.
It's like sending the AI to medical school after it finishes high school.
Yes, perfect analogy. A great example of this is Codex.
Codex.
Yeah, it's a model fine-tuned specifically on billions of lines of computer programming code.
Oh, wow.
A general model might be able to write a simple Python script, but it will probably hallucinate a syntax error. Codex, because it is fine-tuned, is a master at it. Another prime example is Bloomberg GPT.
Which I'm assuming is trained for the finance sector.
Financial jargon, market analysis, economic reports, it's practically a different language.
Oh, I'm sure.
A general AI might mathematically associate the word bear with an animal in the woods, but Bloomberg GPT associates bear with a downward market trend, complex derivatives, and historical financial crashes.
If you are listening to this on your commute or at your desk, this is where it really intersects with your daily life.
How so?
Well, we have this collective assumption that there will just be one big AI that we all consult.
Right, like an oracle.
Exactly. But the reality of the engineering is moving the opposite way. If you are a lawyer, your firm isn't going to use the same AI to review contracts that an advertising agency uses to write catchy slogans.
No, not at all.
You are going to rely on a highly tuned, domain-specific expert.
The education of the model dictates its utility just as much as its architectural blueprint.
Okay, so we have the brain's wiring and we have its education, but how does this intelligence actually interact with the physical world?
That's the next big hurdle.
And practically speaking, where does it live? This brings us to the third crucial layer from our sources: senses, sizes, and access.
And this is arguably where we are seeing the most rapid, disruptive evolution right now.
Let's start with the senses. What does the framework mean by modality?
So historically, models were unimodal, meaning they only processed text. They were brilliant, but they were essentially trapped in a dark room, only able to read notes slipped under the door.
Just text files.
Just text. But now we are moving to multimodal models. We are giving them senses.
Like vision.
We're giving them vision and audio. Models like GPT-4v and Gemini process text alongside images.
But how does that actually work mechanically? I mean, we just said a transformer operates on text tokens and math. It doesn't have an optic nerve. How does an AI see an image?
By translating the physical world into math.
Okay, I'm going to need you to unpack that.
When you feed a multimodal AI an image, it chops that picture up into a grid of tiny patches.
Like a mosaic.
Right. It takes those pixel patches and converts them into mathematical vectors, the exact same kind of vectors it uses for words.
Wait, really?
Yes. So to the transformer brain, a picture of a coffee cup and the word coffee are mapped into the exact same conceptual space.
That is wild.
It really is.
So you could upload a photo of your refrigerator shelves, and the AI can actually calculate what ingredients you have, map those visual vectors to its text vectors, and immediately output a recipe.
It's completely bridging the gap between digital text and the physical environment.
It changes the utility of the tool entirely.
Absolutely.
But speaking of the physical environment, let's talk about the actual hardware these things required, because traditionally these models are absolutely massive. Is the trajectory of AI just building bigger and bigger brains?
For a long time, yes, that was the goal. The industry was obsessed with large-scale models. When we categorize an LLM, we talk about its parameters. You'll see a model named something like LLaMA 65B.
Okay, I hear that word constantly. Parameters. What exactly is a parameter? This model has 1 trillion parameters. What does that physically mean?
Think of a parameter like a synapse in a human brain. It is a connection point where the AI stores a tiny fraction of its learned knowledge.
Okay.
Or, if you prefer an audio analogy, imagine a mixing board in a music studio, but instead of 50 knobs, there are 65 billion tiny dials.
65 billion dials.
Yes, and every time the model trains, it slightly turns those billions of dials up or down to get the perfect output.
Okay, so LLaMA 65B has 65 billion of those little dials constantly adjusting.
Yep.
That sounds like it requires an insane amount of computing power.
Oh, it does. It requires massive server farms, highly specialized microchips, and incredible amounts of electricity.
So I can't run that on my phone.
You cannot run a 65 billion parameter model on a laptop, let alone a phone.
Yeah.
You have to send your request over the internet to a remote data center, wait for the servers to process it, and send the answer back. It's expensive, and there's always latency.
Which explains the massive pivot we are seeing toward SLMs, small language models, like Phi-3.
Exactly.
But here's my pushback. If parameters are what make the AI smart, how do you shrink the brain without making the AI incredibly stupid?
By changing the quality of the education,
Okay, explain.
instead of throwing the entire messy, contradictory internet at a massive model to let it sort things out, engineers are training small language models on highly curated, textbook quality data.
Oh, so pristine data from the start.
Right. By feeding it perfectly structured information, the AI learns the underlying logic of language and reasoning much faster. It doesn't need 65 billion parameters to memorize facts if it has a smaller, highly efficient reasoning engine.
It's working smarter, not harder.
Exactly. And the profound benefit of an SLM is that it is small enough to run on device.
Locally.
Locally. It doesn't need the cloud. It literally lives inside the silicon processor of your smartphone or your laptop. It works instantly, even if you are on an airplane in airplane mode.
That is a staggering shift for productivity, and especially for privacy. But that actually leads perfectly into the final categorization we need to talk about: access and availability.
Because who actually owns these models dictates how we get to use them.
Right. And the landscape seems fiercely divided into 2 camps: proprietary and open source.
Yes. So proprietary models, like Claude or GPT-4, are closed ecosystems. You interact with them through an API and application programming interface.
Can you explain the API concept for someone who isn't a software developer?
Sure. An API is like a digital drive-through window at a fast food restaurant.
Okay.
You pull up, you hand them your order through the window, and the kitchen makes your food and hands you the response back.
Sounds easy enough.
It is, but you are never allowed to step foot inside the kitchen. You can't see the recipe, you can't see the cooks, and you definitely can't change the menu. You just get the final product.
And I'm guessing you have to pay the restaurant every time you use the drive-thru?
Exactly. Every single query. The code, the billions of parameter weights, the dials are completely locked away on the company's private servers.
Contrast that with open source models like Mixtral.
Right. With open source, they don't just give you the burger, they give you the entire blueprint to the kitchen, the exact recipe, and all the raw ingredients.
Wow.
You can download the actual brain of the AI, all of its parameter weights, onto your own servers. You can inspect how it works, modify it, fine-tune it for your specific business, and run it completely independently.
It's really about control and transparency.
Exactly.
If I am a major corporation or like a hospital handling sensitive patient data, I might not want to send all my internal documents through a proprietary drive-through window where I don't control the server.
It's a huge security risk.
Right. An open source model lets me build my own secure kitchen in-house.
And we are also seeing this globalization of access through multilingual models.
Multilingual, right, like MT5 and XLMR.
Yeah, they aren't just translating English into Spanish like a dictionary. They are trained across dozens of languages simultaneously, mapping concepts into a universal mathematical space natively.
So it doesn't have to translate in its head, it just fundamentally thinks in multiple languages.
Precisely, which is the absolute foundation for deploying this technology seamlessly across global infrastructure.
Man, we have covered a massive amount of ground today.
We really have.
We've gone from the core attention mechanism of a transformer to the improv actors and the detectives, the decoders and encoders.
Right.
We've talked about how generalists are being fine-tuned into specialized neurosurgeons, and we've looked at how massive unimodal brains in the cloud are shrinking into multimodal open source brains right in our pockets.
And the final piece of the puzzle to synthesize here is that these categories are not mutually exclusive.
What do you mean?
When you look at the cutting-edge models being released today, they overlap significantly across these boundaries.
Oh, so it's not a menu where you pick just one category.
Exactly. The dominant paradigm of the industry right now is a total synthesis, a model that uses a decoder-only architecture built on a transformer foundation, trained multilingually, and designed to be easily fine-tuned for specialized tasks.
That combination is really driving the current wave of innovation.
It is the ultimate hybrid engine.
Well, as we wrap up this deep dive, I want to leave you with a final thought to mull over, bringing together the last few threads we pulled.
Let's hear it.
We just talked about this intense race towards small language models, these highly efficient AI brains designed to run locally on your own devices. And we combine that with the new multimodal reality models that can process real-time visual input.
Yeah, giving them eyes and ears.
Exactly. If these incredibly powerful AI systems are no longer locked away in distant corporate server farms, if they are running locally right in your pocket and they are constantly taking in the physical world exactly as you do through your phone's camera and microphone, what happens to the boundaries of our daily lives?
That is the million-dollar question.
When your AI is no longer something you log into, but is rather a persistent, localized entity that walks through the world alongside you, disconnected from the internet, but intimately connected to your physical environment, how does that change human productivity?
It changes everything.
And more importantly, how does it reshape our baseline understanding of personal privacy? It is a fascinating, awe-inspiring, and admittedly complex frontier.
It really is.
Thank you so much for joining us for this deep dive. We hope it helped clear the muddy waters of the AI alphabet soup and gave you a real grasp on the mechanics beneath the hood. Keep questioning the information around you, and we'll catch you next time.